Good afternoon, everyone. I hope everyone has had a wonderful week, and we're going to finish RSS 2024 with a short but sweet half-day workshop. And we have really amazing now speakers today, and they're going to be talking about diverse set of task specification for robots. First, we have Hadas join us. She's going to talk to us about some pros and cons of using temporal logic as a formal task specification. Then we're going to have Peter join us at 2:30. He's going to showcase some of his recent works on robot learning from implicit human feedback. The last session before the coffee break, we have Dave join us. He's going to tell us a little bit about some implicit commitment and consequences of using scalar rewards as a task specification. The first session after the coffee break, we have Yonatan join us, showcase some of his recent work on using natural language and videos and the sounds to bring awareness to robots. Last but not least, we have Cédric join us, talk about ways that robot can represent not just humans' intent, but also robots' own goals and how they can learn skills to solve their own goals. A few logistic things before we get started. All the talks will be recorded, and the links will be posted on our website after the workshop. And the panel discussion is not recorded, just to give people free space to talk. But honestly, it's my first time I'm under any panel discussions. I just don't want the internet to see when I mess up. Okay. And we have 25, we're gonna have a 2-minute left sign for the speakers and 1 to 2 questions after each talk. And please feel free to ask questions during the panel discussion. And we have 25 papers, at least 2 reviews per paper. So we really appreciate all the helps our reviewers provided. And the poster session is going to be from 3:30 to 4 during the coffee break. Right outside of Hall B. If you see the orange poster boards, those are our posters. And I hope folks will enjoy the workshop, have a good time. All right, without further ado, let's get started.
I'm Hadas Kress-Gazit. I'm the Jeffrey S. M. Hedrick professor, senior professor at Cornell in mechanical and aerospace engineering. I do work on formal methods for robotics. I'm going to talk about temporal logics today, and I'm happy to chat afterwards. Okay, so let's deal with temporal logic. So that's kind of what I want to talk about a little bit. So I have a few screenshots from the workshop webpage to kind of give you a feel of where I'm going from in the context of this workshop. So this is the discussion topics. The things I really want to talk about are how do I define tasks? So task objectives, environment definitions, all these things. Advantages and drawbacks. So I think it will be, sorry for the snark, but it'll be a little bit maybe refreshing to hear things that actually don't work. So why would you want to use it? Why would you not want to use it? And then I want to talk about what are the things you can do with temporal logic. So actually the topic is the right topic, but all the questions I'm not going to actually answer. So everything I'm not highlighting, I'm actually not going to talk about. Okay, so I'm going to talk about temporal logic. And I'm going to define, I know some of you in the audience may have seen this before. I'm assuming you didn't. I'm going to give you a high-level view of what that means. But before then, just to make the point of these are not useless. These are a few of the systems we've used in the past in my lab, and there are other labs that have used temporal logic to do high-level robot behaviors. So from the top left, which is modular robots, together with Mark Campbell and Mark Yim at Penn. The bottom left, which is was a project with Tom Howard at University of Rochester. Bottom right, swarm behaviors. So you can see we can capture like different types of behaviors. The top right is actually not a video. I didn't post the video, it's still under review, we're still playing around with that. That's kind of a multi-agent or multi-robot situation with different types of robots. The other thing which I will highlight in a little bit is using temporal logic, you can actually provide feedback during the execution about things that might go wrong, and maybe even adjust or fix or repair the task as you're going. So these are a few examples of giving feedback during execution and repairing automatically. The ones on the left are feedback. This is the thing that could go wrong. The ones on the right are, okay, something went wrong, I'm going to fix it by blah, blah, blah. I'm happy to talk about any of these anytime. All right, so really, I don't want to spend time on, I need to show you cool robot videos because we have cool robot videos. So I'm going to show cool robot videos, but really what I want to talk about are the temporal logics and what I can do with them. So this is also from the website for this workshop, and one of the paragraphs in the middle says, to facilitate deep discussion, we break instances of task specification into two complementary groups, formalisms and modalities. So I'm actually going to not accept that definition. I still think there's these two groups makes a lot of sense to me, but what I would call them was formalisms and abstractions or grounding. Those are the words I would use. So we have the how do I write it, and then I have the what does it mean? So those are the things that I'm going to talk about. And if I talk about this in the context of logic, really formalisms goes into syntax. What is the syntax of the task that I can capture? And the abstraction grounding plus the logic structure itself is the semantics. What does it mean? What does it mean in the real world in this case? So I'm going to go with syntax and semantics. All right, so let's talk about specifications. I'm going to show you a little bit of logic. If you've ever seen me give a talk, you've seen one of these slides, so I'm sorry. But what I want to talk about, I want to talk about two types of logics that we use. There are two types of temporal logics that we use. There are many different types. People use some other things, but I think these two have properties that are very interesting for robotics specifically. So I'm going to highlight that. The first one is linear temporal logic. So whenever I talk about a logic, I need to tell you the syntax. What is a valid formula in that logic? What are the symbols I can put together? And then what is the semantics? What does the formula mean? So in the case of LTL, the intertemporal logic LTL, really it's a logic over discrete things. I have propositions. I have these pies on the top left, and these pies have meaning. But if I was to think about it in the context of robotics, I can discretize the state states of the robot, of the environment. Like you could create these symbols that represent what the robot is doing, the environment, goals, blah, blah, blah. And once I have those propositions, when I have that abstraction, now I can start composing interesting things, right? So my 30-second description of what temporal logic is as opposed to Boolean logic, where you have and or not. So you still have propositions. You can combine them using these Boolean operators. So Hadas in Delft is a proposition. It's true today. So the formula Hadas in Delft and Dylan in Delft is true today. But if I think about the world not as a fixed, propositions are either true or false, but all propositions can change with time. Now we can start thinking about temporal aspects. So, for example, always Hadas in Delft and Dylan in Delft. I wish, but no, that formula is false. But if I say eventually Hadas in Delft and Dylan in Delft, that is true because it's true right now. So I can think about these operators. So I have the notion of next. Next is a little bit tricky in robotics, so we can have a conversation about that separately. The box corresponds to always. The diamond corresponds to eventually. And the U corresponds to until. So something has to happen until something else happens. The semantics are defined over infinite traces. So I have infinite assignments to the truth values of the propositions. So for example, that's in Delft. Currently true, will be true in the next hour, will be true in the next hour. Tomorrow morning, whatever, 6 a.m., it's going to be false. Why? Because I need to go home. Okay, so the truth value of the proposition, and then I can start, given an infinite trace of the truth value for the propositions, then I can determine whether formulas are true or false. So a question of, given a formula, I can tell you whether it's true or false, given that they have an infinite trace. But if I kind of plant the seed, then also if I have a formula, I can find a satisfying trace to be able to satisfy that formula. And that's kind of where it becomes useful for robotics. Well, I think it's useful in both ways. But here, the idea is you have to have a discrete abstraction. Now, the more fine-grained the abstraction, the more kind of closer it is to the real world, the less you can compute. It's going to become larger. And vice versa. The more coarse it is, the more I can compute, the more I have to put the weight on the abstraction. Does it actually, is this symbol something I can actually guarantee? So if I want to go from symbol A to symbol A being true to symbol B being true, I need some continuous controller that will do that. And the more coarse it is, the more weight I put on or the more challenge I put on the lower level in the abstraction. So just to give you one example, if I have, imagine I have 9 propositions. Oh, I cut off the thing. Sorry. So I have x's on the x is on the x-axis. Imagine I have y's on the y-axis, and now each region is represented using 2 propositions that are true. So the bottom left is going to be x0, y0. So x0 true, y0 true, everything else false, and so on. So what I can write is starting from x0, y0, so starting from the bottom left corner, always, and, so they have an and, always not x2, y0, so that the region with the red kind of do not enter thing, I never want to go there. And always, well, we'll skip that one, it's a little bit in the details of the specific synthesis algorithm we're using, but always eventually x2, y2, so the top right, and always eventually x0, y0. So this task says I want to infinitely often go between the top left, top right, and the bottom left, and I never want to go to the bottom right. So this will give you a feel for the specification, right? That's kind of this is LTL. All right, so LTL has a bunch of good properties in the sense that I can actually synthesize controllers, or I can synthesize state machines that if I execute them, satisfy my task. But the fundamental thing here is I need an abstraction. I need something discrete. And there's no timing, right? There's no time, explicit time. It's just steps. I'm going to do this, then this, then this, then this. A different logic we've been looking at, and not just us for sure, a whole bunch of groups, is signal temporal logic. Here, instead of, let's see if we can see a mouse. Yeah, there we go. Okay, I want to use my mouse to also people on Zoom can see. So here, instead of this view, instead of now having a discrete abstraction, now really what I'm doing, I'm writing specifications over continuous signals. So this is continuous, in general, could be continuous time, continuous value signals. Really, in practice, it's continuous value, discrete time signals. So basically a signal that can have any value, but this mu predicate is a predicate over that signal. So now I can write, for example, a predicate could be, I'll show you an example. A predicate could be my distance from the table. So I'm moving continuously, so that number changes. But I can say that the predicate is true if the distance between me and the table is less than 1 meter, and the predicate is false if I'm further away. So you need to have this predicate function. You can see that's here in the H. So given a continuous signal and given a predicate function, those are now my building blocks that I'm writing over. The other thing about STL is that it allows me to add timing. So I can put timing intervals, here. So again, I can say always within time A and time B, this has to happen. Eventually between time A and time B, this has to happen. So I can write formulas in STL, and I can evaluate whether they're true or false. The other thing that is actually really awesome about STL is that it also has a quantitative semantics. I can tell you how far away I am from satisfying a specification. For example, if my specification is always Hadas more than 1 meter from the table, then if I don't fall, if I'm here, I can say my robustness is 0.5. Because it's 0.5 until I'm up to kind of almost violating. On the other hand, if I'm very close to the table, my robustness right now is minus 0.9 because I'm literally right next to the table. So the sign of the robustness metric tells you whether it's true or false, but you also have a number that tells you how far you are. So you can think about robustness, which is really nice. Okay, and this would be an example. I think I'm running a little bit late, so let me not go through this example. But this is an example of kind of picking up an object, drop it picking an object, drop it in one of the boxes that we did. And there's a bunch of kind of things here. All right, questions that I get often. Not so much. I wanted to mention PDDL, so the planning domain description language. I keep forgetting what the P is. And it's not PDDL star, but I'm putting a star because it's I'm gonna really generalize here. There are many variants of PDDL. There are things that can do different things. I'm overly generalizing. But really, the way you want to think about this is the basic building blocks in temporal logic are states of the world. The basic building blocks in PDDL are actions, things that change the state of the world from a precondition to a postcondition. Typically, we have, and PDDL allows you to parameterize those, which is really nice. We have formulas, so typically, or let me go with planning. Planning started from the fact that you want to reach a goal state. And for temporal logic, really, you care about the trajectory. So if it's just you want to get to a goal state, temporal logic might not, anyway, there are trade-offs. It's always trade-offs. Temporal logic is good to put constraints. So for example, negations. I don't want something to happen. That's a little more challenging to do in the PDDL kind of planning world. And very often what you would get, again, I'm overgeneralizing because there is contingency planning. There's a bunch of stuff in the planning world, but like the basic original PDDL is you get one plan. While when you synthesize temporal logic, when you synthesize LTL, you typically get multiple plans. You can kind of choose from a bunch of different plans. All right, so I'm going to do just a quick plug for a journal that I used to be on the editorial board of. I really, really like. It's Annual Reviews of Controlled Robotics and Autonomous Systems. And there are a bunch of papers, both on the planning side and on the kind of temporal logic side. One of them is mine, so, which I'm talk about synthesis in this context. So I highly recommend that. The journal in general is really fabulous. So take a look at that. Okay, so hopefully you get a little, for people who've never seen this before, I hope you kind of get a little bit of a feel of what LTL and STL are. And really what I want to do is I want to just give you snippets of what are the things we can do with this. So first thing that's kind of, well, not first, verification. Verification is the process of, given a system, someone already built a system, given a requirement, can I prove, or can I find a counterexample that the system satisfies the requirement? That's verification. I already have the system, I'm checking it. I want to verify it. And there are many, many techniques to do this, and there are probabilistic techniques and so on. But you have to have a requirement. And the requirement is given in temporal logic, typically. So this is, I wanted to kind of, I'll show you snippets of things we can do with this. So this is kind of fairly recent work where we look at a black box controller, and we're able to do this probabilistic verification of a task we're able to do probabilistic verification by both providing the probability of success or the probability of failure of the task and examples of failures. So kind of we can sample from some distribution to show you what the failure modes are. And in this case, we kind of see two different failure modes. I'm not going to go into details of what this is, but obviously, just to give you a little bit of a taste. So yeah. Synthesis is the dual problem. Synthesis is I have a temporal logic formula. Let me generate a system that's provably correct by construction, that will do what I want it to do. Or tell me you can't. That's a process of synthesis. That's the annual review paper I was talking about, that for LTL. The interesting thing that what we've been interested in lately is synthesis, a priori synthesis, and then also synthesis on the fly to repair if something changed. Just to give you a little bit of a feel, the task was pick up an object, put it in the box, and here what we did is we modified the task as it's executing, added basically and avoid obstacles. So it's just a conjunction. We just added a few more symbols to create a totally different behavior. This was the and avoid cones. On the right side, he's going to just introduce another box. So literally, he just wrote a few more symbols in a text file, uploaded it, and then changed the task immediately. And now it's reacting also to where that box is. So we can do this conjunction, we can do disjunction, we can kind of change things on the fly, which we can do because we have this formalism that captures what we want to do. We can provide feedback. We can explain ahead of time why we might not be able to satisfy the task. we can explain as we're going for the STL case, what is the possible failure mode, we call this pre-failure warnings. What might happen now that will make me fail? So we showed kind of, here you'll see, actually, let me skip this. So really what's going on here, I'll skip this. You know, now with the whole, with learning these days, right? So there's a lot of things going on. She's laughing at me. Is there space for these kind of formalism? Why not just learn everything end to end, you know? And you know that I am willing to have a really long conversation about that and my thoughts there. I do have thoughts. But there are some really interesting connections between temporal logic and learning, and especially since it's such a concise and precise way of writing a specification, of explaining what we want to do. So there's a bunch of work. I mean, this is just a random Google. I need to go more deep into what people are doing. It's really cool. In terms of using temporal logic as reward functions, learning them from people, using them to ensure safety of RL. There's a bunch of kind of going back and forth between there's some going back and forth between temporal logic and reward function. And then the final thing that I am, we just submitted a paper on evaluation. That is a big pet peeve of mine right now with reading a lot of papers, the evaluation, especially the kind of the large models. If you write papers on large models and you don't evaluate them, and if you don't spend the same time you use to train it to evaluate it, I have thoughts, okay? So here's this was actually rejected from RSS, and you know, the reviews, they had good points. Resubmitted, I'm gonna probably post it on archive probably tomorrow. But here, what we're looking at right now is we're looking at each line corresponds to a different policy. It doesn't matter what the height, it's just a difference in height because we can see it better. We rolled out a policy using different models. The gray line is 0. It's an STL specification. And everything on the right of it, all the positive numbers, are the specification is satisfied. Everything on the left side, specification is falsified. So the task, the rollout violated this task specification. So you can see the orange policy, and I don't care what the policies are because that was not the point. The orange policy doesn't do quite as well as the blue policy, for example. So the second from the bottom versus the bottom one. The bottom one is never on the left. The orange one is on the left. So I think this is a nice way, and this is, I should also mention, this is all physical robots. This is not simulation. It is much easier to do this in simulation because you have ground truth, because you have basically, you have full information in the simulation, right? So we're thinking about implementing this as well. But even for physical robots, we can do this. So I think that was something that I'm going to start pushing because I think it's cool, but we'll see what the community thinks about it. Okay, to summarize, and I don't know if I'm good on time. Look at that. Even with the technical stuff, just talk fast. So summary. Temporal logics are expressive. They can capture a lot of things we care about. We care about goals, things that the robot eventually can do. We care about constraints, things that the robot should not do, right? I don't want you to run into the wall. Now, do I want to specify that in temporal logic? No. But if I have a specification that is follow a person, but you know, if there's an alarm, I want you to follow them. I want to follow in front of them. But if there's no alarm, I want you to follow them in the back. Or if there's an alarm, I want you to lead them. If there's no alarm, I want you to follow them. That's a longer collision avoidance, and that is super, super easy to specify in STL. We have actually another rejected paper from RSS with kind of a user study that we did with STL. So there's a lot of things we can express. They are useful for different settings, for different problems that we might want to have. So verification, synthesis, I think they have a place in learning and evaluation and all that. But nothing is perfect, right? Nothing is perfect. Nothing is a silver. There are no silver bullets, okay? So what are the drawbacks of temporal logic? So for LTL, abstraction. Like I said in the beginning, the more fine-grained the abstraction, the easier it is to match to the ground in the real world, the more we're going to run into the second issue of scalability. So there's this trade-off of abstraction scalability. Because if I could abstract the world into 0.1 centimeter voxels, the whole world, and write a specification on that, awesome. I can definitely do that. The connection between the symbolic and the physical is really, really easy. There's no way I'm computing that ever, ever, ever. Okay, so there's a trade-off of abstraction and scalability. And then, why did I write preferences? Now I don't remember why I wrote preferences. So I think, I know I wrote that. So currently in using LTL and STL and using these temporal logics, it's not so much the formalism, but if you want to have, it's more kind of the algorithms that you use, so verification and synthesis. If you want to have like hard constraints and soft constraints, if you want something that are just like optimization, STL a little bit better because STL you solve as an optimization problem, so you can put an objective that's more interesting or not that has to do with preferences. You can also always have like another input that says, if this is true, then ignore that. So there are ways around it, but it's not the most natural in terms of capturing soft and hard constraints. But I think that's my spiel. Thank you so much.
In the interest of time, can we have just one question from the audience? Yes.
You mentioned that you are highlighting these two temporal logics specifically because they are nicer for robotics. Can you elaborate on what makes temporal logics nice or not so nice?
Okay, so the question was, I'm just going to repeat for the Zoom people. The question was, I mentioned that LTL and STL are nice for robotics. What about other logics? Are they not as nice for robotics? It's not that they're not as nice, but LTL and STL also have trade-offs. So LTL I can synthesize ahead of time, and I know ahead of time whether I can perform the task or not if the abstraction is accurate. STL typically is done like it's an optimization problem that's done on the fly, so it's hard for me to give. There are some ways to give guarantees over a finite horizon. You can provide a little bit less guarantees a priori, but they capture different aspects of robotics in the sense of STL is better for kind of leaning into the continuous versus LTL gives you a little more guarantees. Other logics have time. So there's like logics that have discrete abstraction, but they have time. I can still use that, but it's not farther enough from LTL that I would want to use that, right? There are other logics. I think these two captures, like, it's not that the other ones are not good, but these ones have been used, and we have algorithms to actually synthesize robot controllers from this, and it's kind of a little bit better understood. You can think about the thing that they don't have parametrization. But then you go into logic that are much harder to deal with because you start going to first order logics, which is, synthesis there is intractable. So there's a trade-off here, and those two kind of capture different subsets of the world that would be useful. Not necessarily that others are bad, but these are kind of capturing good subsets, I think. Yeah. Another question? Can I take it? I take one more question.
Okay, sure.
Go ahead. Yeah.
Yeah, I'm at the verge for robotics and also the software community, and there in formal methods, there is some work to try to create patterns applied to robotic missions concretely using the linear temporal logic. And so I was wondering in regarding to this parameterization, or because this can become arbitrarily complex depending on so if the mission is really complex and with the level of abstraction, it can be arbitrarily complex. So they try to create this collection of patterns that represent most general robotic missions. Do you see any connection value in generating as a community such a collection of patterns to accelerate the work on validation using methods like the temporal logic, for example, so that we share the patterns in which we describe our constraints, for example, instead of using, you can describe it in different ways, depending on what the task is. Your opinion.
So the question is it? I'm going to rephrase a little bit and let me know if I misunderstood you. The question was about patterns. Can I generate a priori formulas that represent different aspects of robotics, and then I just mix and match? I don't know that so I don't know enough about this. I think if it helps with scalability, meaning the pattern itself, I don't see that as quite as useful. If there are methods for me to pick and choose different patterns and just automatically generate the automata that satisfies those in a way that's much more computationally efficient, yes, absolutely. I think that would be awesome. Yeah. So it's more the synthesis part, the getting the specific, getting getting the system, the scalability there, not so much the writing the specification itself. Yeah. Okay, now I'm done. Thank you, everyone.
Okay, our next speaker will be Professor Peter Stone. Peter is the founder and director of Learning Agent Research Group at UT Austin, as well as Associate Department Chair and Director of Texas Robotics. His main research interest in AI is understanding how we can best create complete intelligent agent. And thank you for taking time out of your schedule for coaching RoboCup. And today he's going to talk about human-in-the-loop learning for robot navigation and task learning from implicit human feedback. Let's welcome Peter.
Okay. Thank you very much for the invitation. And I'm sorry I can't be there in person. I was hoping to. I'm actually relatively nearby. I'm in Eindhoven, which would only be an hour and a 15-minute train ride if I were near the central station, and so were you. But all in all, it would have taken too long for me to get there and back and still be here for things I need to be at. I'm here in Eindhoven for RoboCup. And I have a bunch of things I could say about this fun topic on task specification. And so, but I'm going to take advantage of the fact that I'm here at RoboCup to sort of show you some things that have happened just this morning that are relevant to this. I will say, Hadas, I think probably the reason you put preferences up on your slide at the end was that I'm going to say some things about preferences at the end. So thanks for setting that up for me. Yeah, good thinking. So I do, well, yeah, so actually I'll just jump to, you know, I am here at RoboCup, and you know, RoboCup is usually started as robot soccer, where the task specification in some ways is quite simple. It's just win the game. But it actually gets much more complex than that when you sort of drill down. There's, you know, score the next goal, or there's defend against that kind of a shot. There's all kinds of different task specifications that can be given. I'm not actually going to talk about soccer. I have a team in the robot soccer competition, but also in this video that I have up here in the RoboCup at home competition. And this is for those of you who aren't familiar, it's something where you have to have a robot that's that does sort of domestic tasks. And I think actually I won't, yeah, so this is our robot, and it was in a task called general purpose service robots, where the robot has to come into the room and then listen to a person just tell it its task in natural language. But I think you maybe be able to hear it here. Okay, we can't really hear the audio. That's what I thought. So I'm going to turn off the audio. And I'll just tell you what the task was. The person there said, tell me how many standing persons are in the office. And oops, and the video jumped back. So the person said, yeah, tell me how many standing persons are in the office. The robot repeated back, you know, is that what you, did you ask me to go tell me how many standing persons are in the office? The referee in the red shirt said yes. And then the robot needed to navigate back into the office and look there around where there are two standing people and one person sitting, had to look around. And it didn't know that this was the command it was going to be given. There's a large space of possible commands that the robot could be given. And it has to do as many tasks as it can in a 5-minute period. And so here it did, it looked around, it's now going to go back and report back to the referee. And in fact, in this case, it didn't quite get it right. It came back and said there was one person standing, and it said it in natural language as well. And so this was the task specification here, though, is just plain natural language. And the other 4 tasks we were given over 2 possible runs are shown here. Tell me what is the heaviest fruit on the desk. So it had to go navigate, see that there was an apple and a lemon, know that the apple was heavier. Then it was told to fetch a drink from the shelf and place it on the TV table, or tell the gesture of the person at the kitchen counter to the person at the shelf. And then in that case, there was a person standing, raising his right arm. And then also tell me what's the heaviest object on the kitchen cabinet. So this is sort of to me, the kind of task specification we've always dreamt of being able to use in AI. Just plain natural language in a huge space of possible tasks, and the robot needs to not only understand it in natural language, it needs to do online planning, execute the task, and then come back and report in natural language. And so, this isn't actually at all what I was planning to talk with you about, but I was thinking about the topic of this workshop as this was happening this morning, and thought I'd share that with you. But going back to what I did plan to say, and sort of in the interest of time, I'll skip through some things. Usually in a talk like this, I tell you all the great things that are, that are happening here at UT Austin. We've got we have an AI institute and a beautiful new space for Texas robotics. I tell you about my overall research question, which you can find in some of the other talks I have online, but it's all about multi-agent systems, reinforcement learning, and robotics. But for this talk, I'm sort of actually going to give a brief summary of a bunch of different lines of work, but reframing them in the context of how the tasks are specified. And in contrast to sort of the sort of most run of the mill way, or the most traditional way, at least in reinforcement learning, of just giving a scalar reward, which would be akin to, in the robot soccer case, just saying win the game and no other information. When it comes to human in the loop learning, though, an area that I've been involved in for now 15 years or so, it gets much more interesting than that. It's not just that there's a reward, a scalar reward signal, but there can also be input from a person in different forms. And my first sort of foray into this, which I'm not going to talk about in detail, but was the Tamer system that was introduced by Brad Knox in his PhD thesis, which gave the ability for a person to give the sort of a replacement for reward in a reinforcement learning system. And so it wasn't just this environmental signal, but rather a person being able to say good job or bad job. And in some sense, the task was specified in that way. And this was extended to, it was first done in the Tetris setting. I'll show you an example of that, extended to learning from pixels about a decade later. And then also we've done some work on sort of a related modality of human in the loop learning of imitation from observation, where the task specification is just get as close as possible as to the task that you're observing, that a person do. And this was the PhD thesis of Faraz Tarabi more than 5 years ago now. And just to give the sense for those of you who aren't familiar, in sort of our original Tetris system for Tamer, rather than saying what you would traditionally say is like clear as many lines as possible in the game of Tetris, instead there's a person here who can say good job or bad job. The square up in the top left flashes red when a person is saying bad job, and green when the person is saying good job. And the finding, and so this was an alternate, we didn't think of this as a task specification question. We thought of this as sort of an alternate paradigm for reinforcement learning. But in some sense, that's exactly what this was, is a way of specifying the task through human preferences, or in this case, just positive and negative feedback. And the really nice result here was that, even in the first game, which was shown here, I get this, 1 second. Sometimes the video hangs. It was starting to do much better than random in a setting where, using the traditional task specification of just how many lines have you cleared, it would take hundreds of thousands of games to get really good performance. This is a video of what would happen after just 3 games, 3 episodes of a person giving that positive and negative feedback, and it's already playing the game quite effectively. And so what we learned was that Tamer learned much more quickly with this task specification, not in asymptotically, not as well as the autonomous learners that were doing it from the traditional task specification of just 1 point for clearing each line or something like that. But then we did look at how can these be merged, and how can we take this to video input. And in some sense, we didn't name it this in the end, but this was really the first instance of reinforcement learning from human feedback, which is known now as RLHF, and played a big role in the success of ChatGPT, and has inspired a bunch of research, additional research that I'm going to touch on before the end of the talk. And then, as I mentioned, there's also that's when the person is just saying good job or bad job after every action. Then another task specification that's been explored extensively is the imitation learning. That can be learning from demonstrations, where what you get is the actual actions that a robot took at every particular state. The twist on that Faraz, shown here, did in his PhD thesis in collaboration with Garrett Warnell and myself, was that we were doing imitation from just observations, where we didn't know what actions the agent took. We just got to see the sequence of states that they went through. So the same thing, like, you know, if you're watching a fitness instructor and they start doing jumping jacks, right? You don't know what motor impulses they sent to their arms and legs, or what signals from their brain, but you can see what they do and you can try to imitate it just from observation. So we introduced a model-free method, or a model-based method known as behavioral cloning from observations, and a model-free method, generative adversarial imitation from observation, that sort of opened up the space of a task specification of just trying to imitate the sequence of states that are observed over time. What I'm going to dive into a little bit in a little bit more detail is some more recent work than those. Very much in the same vein of these, learning from human feedback. I'm going to talk about some work with Trace Zhao on human in the loop learning for robot navigation, and this is robot navigation is one of the most sort of long-standing tasks in artificial intelligence. It's get your robot from a particular place to another particular place, and the traditional task specification is just the XY coordinate that you're trying to get to, or the location that you're trying to navigate to. That's the global goal. But of course, this can also be decomposed, into maybe first having you can do path planning and come up with a global path, and then that becomes the task specification of just follow this blue line, follow the path that I have planned. Or you can you can have waypoints along that line, which are the sort of the local navigation targets, and that becomes the task specification for a short period of time in sort of a temporal abstraction kind of setting. And then there's even below that, there is a task specification of the motion commands. Like, I want to accelerate and turn to the left, and that's a task specification for a PID controller. And so there's this task of robot navigation can be decomposed into these different task specifications of motion control, local planning, and global planning. And then and that's even in sort of the business as usual kind of way, but then connecting back to Tamer and imitation from observation. And I apologize again, I'm skipping through like a presentation where I would talk about all the technical details of this to just highlight the task specification aspects, which is where we first of all we were looking at this in the setting of navigation in highly constrained environments. This is actually an aspect of robot navigation that's not completely solved. Like, you can navigation on a road or in a relatively open space is not, I wouldn't say completely solved, but fairly fairly well studied and with very mature technologies. But when you have spaces that are barely bigger than the robot that it has to navigate through, navigation is still quite a challenge. And then, of course, there's also social navigation when you have to navigate with people and dynamic objects. But here we're focusing mainly on the highly constrained environments. And in those settings, classical motion planners that sort of using the paradigm I just showed require a lot of computation, so can slow down the robot. People have been looking at learning-based planners, but they need a lot of training data. And so we were looking for sort of hybrid approaches, and really then task specification ended up playing a really big role. This is, by the way, Shuisu Zhao, who's faculty at George Mason now, has been leading a series of robot competitions for robots navigating through highly constrained spaces. So here you see the robot and the sort of the maze that they have had to navigate through at a series of ICRA conferences. It's called the Barn Challenge. Encourage you to join. It's got a simulator where you can test technologies, and then the ones that do best in the simulator are invited to deploy them on a real robot. But our approach to this kind of a problem we've called adaptive planner parameter learning. And again, without going into the details of all of the different sort of sub approaches here. This slide summarizes the different ways that we've specified the task beyond just get to the global goal or even the local goal. There's teleoperated demonstrations in a method called APPLE-D, Adaptive Planner Parameter Learning from Demonstrations, where the task is specified first by a person teleoperating the robot through the constrained environment, which gives sort of gives clues on where you need to drive more slowly and more carefully, like through the narrow corridor, and where can you speed up and drive with a little less, with a little less care, and then that provides a specification of the task that we use to try to come up with the planner parameters. I'll talk about exactly what that means on the next slide. But then similarly, we've looked at not just demonstrations, at corrective interventions in this video on the top right, where a person doesn't give full teleoperations, but just steps in and corrects the robot when it does something wrong. And we in that work, we specified two different types of interventions. One's where the robot is going to take a wrong path, maybe run into a wall. Those are the ones we call type A interventions. And then or others where it's using a perfectly fine path, but it's moving too slowly, which we called type B. And so again, the task specification here was in some sense, do what you would normally do, except in the cases when I've taken control and said you're doing the wrong thing, and try to learn from that, try to generalize, try to, the specification is in some sense, learn where I would intervene and then drive more like me, but otherwise do what your default policy says. Which is actually quite an interesting task specification, I think, because it depends on what the default policy is. And then there's the one on the bottom left, which is evaluative feedback. That's more like the tamer setting, where a person is just saying good job and bad job as the robot is driving. And then there's the traditional reinforcement learning one, where in the bottom right, where it's just learn from its own, from all of your own experience. And the thing in common for all of these approaches was, rather than learning, we are taking an existing path planner, global planner, and local planner, like a whole navigation stack. It's the Ross move-based navigation stack. And rather than throwing it out and learning end to end, rather just learning the parameters of that navigation stack. And so, in learning language, you would normally do, you could think of end-to-end learning as trying to learn a motion policy. In contrast to that, what we're learning is a parameter policy. We're sort of putting the classical motion planner itself in the environment and saying that the thing we have control over in our policy is the parameters. And so when we're doing learning from demonstration, we're trying to learn at this parameter space, what are the parameters of our motion planner that lead the planner to look most like the human demonstration. And similarly for the interventions or the evaluative feedback. And so, all of this is, in the end, we have we try to put all these together so that the robot can learn from the traditional reinforcement learning sort of back in the factory when it's got lots of time for experience, and then be put in someone's home and learn from all of these modalities or these different, more creative task specifications of demonstration, intervention, and evaluative feedback in sort of what we call a cycle of learning. And again, I could give a whole talk on the technical details, but again, this is mostly just about the task specification aspects of it. If you're interested, Shreesu put a really nice website together on Apple, APPL, for Adaptive Planner Parameter Learning. The other, then, to completely shift gears, well, not completely, but to shift gears to a different talk, but still in this space of task specification from human interaction. There's a paper that we had in Coral not too long ago with some colleagues. First author was again Brad Knox, the initiator of Tamer. He's actually been involved in all of this work. We introduced what we call the empathic framework for task learning from implicit human feedback, with the idea that that a lot of learning we do as people is through sort of verbal signals or body language. You can sort of learn a lot from a person just by looking at the pose of their body and those kinds of things. You can probably look at this video and guess that the car is probably doing something wrong. The people don't have to say anything or reprogram the car. The car ought to be able to say, don't do that as much. Or you can even look at the pedestrians outside and try to say, is this car making this guy nervous or not? And so this was the sort of the motivation behind learning from implicit human feedback. We introduced a problem called the life problem, or learning from implicit human feedback. We formalize it in the paper, and then introduce a framework called empathic. There's a clever acronym that I forget, but that basically is it was designed to learn from watching a person's facial features, and it has two stages. One is for tasks where we know what the right thing to do is. We just train a camera on a person's face and try to learn a mapping from what a face looks like when the robot's doing the right thing versus what it looks like when the robot's doing the wrong thing, which is actually a lot trickier than you might think. Some people smile when the robot crashes into a wall, and but it's maybe a different kind of smile than when the robot reaches the goal. And then the second phase is you take that learned mapping, that sort of the reaction feature extraction module and the reaction feature vector that we learn, and especially this mapping to reaction features, and then use that as, in some sense, the task specification. Tell the robot, just do the actions that will lead to the most positive facial expressions of your user. And here's the acronym for empathic. It was a evaluative mapping for effective task learning via human implicit cues. And again, interest of time, I won't go into all the technical details of it, but just to say, I think I have a nice, here's a video of what you might be looking at. And the first step of this research was we checked to see whether there's signal in watching faces. And so we did like a human proxy experiment. We would be asking you as a user, can you look at these faces and figure out when the robot did the right thing, when a good thing happened and when a bad thing happened? And it's not easy, it's not straightforward. But in the end, people are able to do it better than random. It's certainly not as good as positive and negative feedback. And we were able to show in this paper that we could get enough signal out of this as the task specification, that we could learn behaviors in a number of different tasks. One was a sort of a control a taxi in an environment domain, and another was a robot sort of recycling sorting domain. I don't know if I can. Well, yeah, this was the taxi domain where you have a taxi that has to navigate around an environment and pick up passengers without running into obstacles. But it was trying to learn what to do just by looking at the people's faces. Here's a relatively easy to read expression, but some of the others are much more difficult. And then the other task, and again, I'm skipping through the details of this. They're all in the paper. But I think, so the other task was sort of a recycling task where we had a robot trying to put objects into different bins, and its only task specification, it didn't know what the objects were, it didn't know what the bins were, it just had to watch a person's facial expression to understand whether it had done something right or wrong and learn from that over time. And then finally, I think I know I'm running out of time, but the last sort of vignette, and this is where all of this sort of does come down to preferences. And so this is Brad Knox again. I'm using his slides here on a recent sort of talk that he gave. But it's really, you can think about all of this human in the loop learning. In the settings that I gave you, it was, a person giving demonstrations, interactions, evaluative feedback. One of the most sort of active and I think interesting task specification languages now is human preferences, where what the way the task is specified is you get pairs of behaviors and you need to indicate which one you prefer. You don't really say good, absolutely, or bad, absolutely. You're just saying among two options, which one is preferable. And that's how RLHF really works for fine-tuning large language models. The human is given a positive, a couple of different outputs. They say which one they prefer. You get a large database of that, and so that ends up being the task specification. There's no reward signal. There's no demonstrations. It's just preferences. And so I'll give you one sort of technical insight that we had here. First, learning from preferences is that there is some preference model, which that says given some reward function, you can say whether one trajectory is preferred to another trajectory, So that's a preference model. And learning from preferences, your goal is to be, if you're given a bunch of pairs of examples of trajectory 1 great is preferable to trajectory 2, can you infer what the actual reward function, the underlying reward function is? And then you could do traditional reinforcement learning with that reinforcement learning. So you want to optimize your estimated reward function to maximize the likelihood of the preferences that were expressed by the person who is expressing them. And so there's a number of different models of preferences. Again, due to time, I'll refer you to the papers for a lot of the details. But what we can do is think of it being as a person has a sort of hidden reward function in their head. We show them a bunch of pairs of behaviors and say, which one do you prefer? And then we try to go back and induce and estimate what that reward function was, with the idea that once we know the reward function, we can do learning. Yes, 2 minutes, good. So the sort of traditional way, and actually the way that people have described doing preference model learning, is that they say that the probability that preference 1, that trajectory 1 is preferred over trajectory 2 is if the reward that you get while you follow trajectory 1, which is the sequence, the reward for the state action pairs, how much better is that than the reward you would get while following trajectory 2? And so it basically, but it turns out, I mean, it seems intuitive, but it turns out that's we think not a great model of what people do when they're giving preferences, in particular, because if you're in this task where you're at the blue dot and you have it's specified, the true reward function is you get a -1 until you get to the goal. These two trajectories would be rated equally. In both cases, you get a -2 over their trajectories, right? They don't, they don't tell you anything about how much progress you're making. And so we proposed a new model called the regret model, which takes into account the estimated sort of value of the start state and the estimated value of the end state, and the difference between them, or the progress that you've made along the way. And the regret of a segment, then we model it as measuring how much it deviates from optimal behavior. So in this case, the same example, you'd be getting -2 for this case, because the optimal behavior is to go towards the goal, and this you'd be getting 0 because you're actually doing an optimal behavior. And if we model that's what people are doing when they say which trajectory they prefer, we can get back to something that's closer to their true reward function. And we analyze this both theoretically and through experiments. This is basically it's ongoing research. Our hypothesis is that we've evaluated is that annotators, when we're asking them for their preferences, give the preferences based on the regret model, and that engineers using fine-tuning are unknowingly applying this regret for preference model, even though in their papers they're often saying that they're using the partial return model. And I know I have to end here, so it turns I'll hopefully use that as a teaser to read the paper and look more at why this matters and why we think this matters. I guess it boils down to the idea that large language models are not actually bandits. There are dialogue is a sequential problem, whereas in the ChatGPT paper they say that they model the environment as if it were a bandit. I can talk more about that offline. I know time is up, so I'll just thank you again for the invitation, for your attention, and pop back up to say this was really the whole theme of this talk was looking at how human in the loop learning, in the how I talked about it as it pertains to robot navigation and learning from implicit feedback and model learning from preferences, can all be thought of as being about how do you specify your task differently from the sort of traditional pure reward function in reinforcement learning. Thank you.
Thank you. Let's give Peter a round of applause. Let's take some questions.
Yeah, so thanks for that really interesting talk. I guess I just have a more general question about the direction of AI. Do you think that these robots that can learn online, as you're deploying them, what do you think are the prospects of that? I guess just related to safety. And obviously they have a lot of I want to have your thoughts on whether you think that's the way to happen.
Yeah, in some sense, the whole motivation for this line of human in the loop learning is to sort of change from the paradigm where a robot has to learn its behavior in the factory, and then go into your home with a fixed behavior. And then if you want to change it, you have to bring back a programmer or somebody with robot expertise. Change that to a paradigm where you might start there, you might learn from that as, for your base behaviors, but then, when the robot's deployed in, not my home where I can know how to program the robot, but in my, my mother's home or in somebody, I don't mean to throw my mother under the bus, but she's not going to program the robot. So how can she give a signal of what she wants the robot to do without having to to go back to the program level. And so I think we need that. I think it's not now you're right that safety is a concern, and so you have to be able to do this in a way that is not going to go into sort of horrible spaces of the learning space. But we need, there's no way we're going to be able to train robots to operate correctly in every environment in the factory. They need to be able to do it at deployment time. And this learning from human preferences is all about that.
Thank you.
Thank you. Let's give Peter another round of applause. Thank you.
Thank you.
Our next speaker, David Abel, is a senior research scientist at DeepMind in London. His research focuses on bringing clarity to the central philosophical questions surrounding agency, computation, and learning. And today he's going to talk about the reward hypothesis. Let's welcome David.
I first want to thank all the organizers. It's been a really fun event so far. I've just been taking a lot of inspiration from the earlier talks and lots of questions I want to think about. I'd love to discuss more with you all soon. This is a clicker, perfect. Okay, so I'm going to talk to you about the reward hypothesis. This is joint with a bunch of collaborators across a bunch of institutions. We've been doing this work over a number of years, started back in 2020. The motivation for this work really stems from the need for definitions. So a lot of my recent work has been unified under the theme of trying to provide definitions that I think provide a lot of clarity and a cleanliness and tidiness to kind of the foundations of the field. So I love this quote from Will Quine, who says, "The less a science is advanced, the more its terminology rests on an uncritical assumption of mutual understanding." This really speaks to the state that a lot of kind of younger scientific fields find themselves in, where they're still sorting through the paradigm. They're still figuring out what are the central definitions, models, tools, and so on that the field just sort of organize around. And of course, within AI, we have this big definition of intelligence that people have been debating since maybe the field's founding in the 1950s. But similarly, I think things like the definition of an agent, or perhaps the definition of learning and the definition of goals or tasks are still sort of up for debate. And I'm really excited about this workshop as a space to think carefully about what could we mean by goal, what could we mean by task, what are the pros and cons of adopting different perspectives on what we mean by these different concepts. And so a lot of my recent work has been trying to dig into this question about what is the definition of an agent and goal. And my preferred definition of agent comes from this Richens and Everett paper and this earlier book by Dan Dennett, which says agents are goal-directed adaptive systems. But this partially kicks the can down the road and says, gosh, we first need a definition of goal-directedness in order to really get our hands on a clean definition of agent. So that's where we find ourselves today. How can we first cleanly think about the question, what are goals? What are the possible options of how we can understand what a goal or a task is? And one proposal comes from Rich Sutton, which is the reward hypothesis, which says roughly that we can think about goals or purposes in terms of the maximization of reward. Now, this hypothesis, I tend to think about it, and when we're thinking about specifying a task for a robot, we imagine a task designer, Alice, that has some space of possible goals she has in mind that she'd like a robot to pursue. That Alice can write down a reward function in some form, some representation, that can produce signal for some learning system that can, given access to that signal throughout the robot's experience, can eventually come up with a solution to that task. That's how I tend to think about what the reward hypothesis is saying. No matter what goal Alice starts with, Bob can eventually solve that goal. Now, roughly this means what we're going to study when we study the reward hypothesis is just this simple statement. Can all goals be written down in terms of a reward signal to be maximized, yes or no? And that's roughly the goal of this work. We want to treat this as a genuine scientific hypothesis. We want to ask, can we somehow falsify this hypothesis? Can we find supporting evidence for it? What are the conditions under which it holds? What are the limitations of reward? And the main result we're going to build to in this talk is to identify some precise conditions that tell us exactly when the hypothesis is true. And if it were sort of unambiguously true, then there wouldn't be any conditions. And so I'll just say right now, the hypothesis is false in a certain sense. There are some weird edge cases in which the hypothesis fails to hold. But what I found as I've kind of been working on this and talking to folks about this work is that often these edge cases are the ones where we say, well, those aren't really interesting anyway, are they? And so it's kind of up to us to interpret whether or not we think that these edge cases are meaningful or not. I happen to think they are quite meaningful. Okay, so the way we're going to, yeah, can you hear me in the mic? That sounds good. Okay, perfect. So the way we're going to organize this result is in terms of a number of doors that you're allowed to walk through if you want to reject the hypothesis. And these will roughly be the assumptions that we can make that can get us away from having to accept that the reward hypothesis is true. So we'll reveal a few different doors of two kinds. The first set of doors are ways of interpreting what the hypothesis means. I think there's a lot of room for interpretation in this original kind of natural language statement, the hypothesis, and that's what these first two doors will give us. The second set of doors will then evaluate the hypothesis, given that we've already made a commitment about how to interpret the hypothesis. And so you can kind of decide for yourself which of these doors you might want to walk through as a way to reject the hypothesis. And then if you don't walk through any, you kind of have to accept that the hypothesis is true. Okay, so let's get some notation on the board in order to make some of these claims a little bit more precise. This is going to be a particular flavor of reinforcement learning, largely inspired by this line of work on general RL from Marcus Hutter and colleagues, as well as recent work from Ben Van Roy's group. So we start from an interface, which is a set of actions A and a set of observations O. These give us a set of histories. These are just sequences of action observation pairs of arbitrary length. This will give us an environment, which is a function from any length history and the agent's latest action to a distribution over observations. And then a policy is going to be a history-based function that for each history assigns a distribution over actions. So this is going to capture something like the reinforcement learning problem, but so far we haven't mentioned rewards or goals at all. We just have these two history-based functions exchanging action signals and observation signals back and forth. Okay, so our rewards are going to be captured by these Markov functions. So they'll just take the last action and observation. We'll talk about history-based rewards a little bit throughout the talk, but we'll be most interested in Markov rewards and asking about their expressive power. We'll also introduce a action and observation condition discount. This is proposed by Martha White in this really cool paper on task specification. And we'll adopt that convention, which will give us additional flexibility for grounding goals into rewards. That will give us a specific notion of a value function. I just write this out because we're going to need this as part of our efforts to interpret the hypothesis more precisely. So this is our traditional notion of value. It's expected cumulative discounted reward. But notice that we have this product over discounts as well, since the discount now depends on the action observation pair. And as a special case, of course, we can assign a constant to all actions and observations, and we recover traditional value. Okay, so that's basically it for notation. We'll come back to the pieces that we need later on. But for now, let's look at the first two doors, which are ways to interpret what the hypothesis could mean. So what we're going to get at the end of this is a conjecture that we think captures the spirit of what the reward hypothesis is proposing. So recall, this is the hypothesis. And our first door is going to really ask, what exactly could we mean by goals and purposes, if not reward? I've heard Rich say, we can think about reward as the atomic unit of what a goal is. And if we're asking about whether rewards can capture goals, we need some other language to talk about goals, like perhaps forms of temporal logic. We're going to adopt the perspective of thinking about preferences in their most general form as a notion of goal or purpose. So any preference relation over outcomes is a form of goal or purpose. I think this is sort of a separate hypothesis we're proposing in the background that we need to get this work off the ground. Would love to talk about that more, because I think there's a genuine question to be had of whether this is a sufficiently expressive language as well to think about goals. What that means is we'll start with some set of outcomes. So a classical example is to say, I prefer, say, an orange to an apple. We'll use this little greater than symbol to indicate that, and we'll refer to this as the preference relation. We can, of course, extend this to things like Carrot Bandits, where you might have a selection of options, and then you prefer, say, the pie to the sandwich. We can use the same preference relation in things like chess, where you prefer one state to another, perhaps where your side of the board is in an advantageous position. And we can generalize this to the history-based case, where you just say you prefer one history to another. So our most general form of preferences is going to be preference over arbitrary histories. So that's the first door. The second door is really digging into this part of the hypothesis that says well thought of. So what would it mean for a goal or purpose, in our case, a preference relation, to be well thought of in terms of the maximization of reward? And for us, what that's going to mean is that the preferences can be captured by rewards in some way. So this part will need a little bit more detail to get into, but that's the high-level picture. Can we somehow communicate a preference relation with an arbitrary reward function and discount? So the way we make this more precise is by saying, for any choice of a preference relation, there will always exist a pair for reward function and discount that captures the preference relation. And what we mean when we say it captures the preference relation is that there will be an equivalence between our preferences over policies, those history-based functions, and the values that we assign to those policies. So if this relationship holds, then we will say that the general statement holds. So we're getting pretty close to a conjecture. At some point, we'll just replace this for all and there exists with actual quantifiers over these sets, and that will give us the more formal statement. I'll need to say a little bit more about these policy preferences and values, but the details are roughly what you'd expect. We'll start by talking about these policy values. These are going to be n-step policy values, and we'll have a little bit more to say about n in a moment. But policy preference are sort of funny objects, so let's make that a little bit more precise. Really what we mean by a policy preference is a preference over the outcomes produced by those policies. So for any given two policies, we can think about the distribution of outcomes generated by those policies. And that can be captured at a particular length history, n, by this quantity dn pi. So this is just with what probability will this policy and this environment produce this history of length n in this environment. So that allows us to think about the outcomes of a particular length. In order to get the more general notion of policy outcomes, we can talk about the preference between outcomes at a particular point in time, and we'll generalize this in a moment. So what we will mean when we talk about this coherence is that the value at length n is equivalent to our outcomes of the distribution of our outcomes of length n. The final little nuance, there's a few little subtleties along the way, is that we need to be able to talk about all n larger than some n. And so what this roughly tells us is that the preferences are kind of finitely we can evaluate them in finite time. There is some n where we don't need to look past it in order to determine whether we prefer one policy to another. And I was thinking during Hadas's talk whether how our results will relate to linear temporal logic. And my thinking was this might be the departure point, that temporal logic will go beyond what we do here. So to make this more precise, we'll say there must exist some point in time such that forever after, the policy outcomes, our preferences, and the values agree with each other. That means they're allowed to switch before that finite point in time. So for instance, you could like how the orange hiker reaches a particular destination, but you could like where the purple hiker gets to in the end, as long as eventually you prefer one to the other. And this gets away from a lot of really peculiar cases of preference relations, for instance, where you prefer odd length histories to even length histories. There's all sorts of weird cases that this gets us away from. Okay, so now we're just about to the formal conjecture. We say for every preference relation, there must exist a reward function discount pair such that this relation holds. Our policy outcomes are agreed with by the way we assign value for all n greater than some n. So that gives us this following conjecture. And again, these two quantities are just the outcomes and the value. So those are the first two doors. You might disagree with how we've chosen to interpret the hypothesis, but we suggest this is at least one natural way to ground out some of the details of the hypothesis to study it in more detail. So the next step is now to prove whether this hypothesis is true or false. And that's going to be the second set of doors. But you might already have decided, you might have walked through one of those first doors and just disagree with how we're choosing to interpret the hypothesis. Okay, so now for the second set of doors, we can see right away that this conjecture, as stated, is false, because the way the conjecture starts is far too general. It's for every preference relation. But so far, we haven't really done anything to rule out peculiar preference relations aside from get rid of those that finite evaluation condition. And so, for instance, we could imagine an intransitive preference relation. You might prefer oranges to apples, apples to grapes, and grapes to oranges. There's nothing to stop us from writing down that preference relation so far. And so this little counterexample is sort of hinting at some of the conditions we're going to need in order to close the loop on this conjecture. But in its most general form, we'll see that there are a variety of counterexamples that make this conjecture false. So what we'll need are a set of constraints on the preference relations such that we can recover a reward function and a discount pair. And those constraints are going to be the next 5 doors. You can choose to accept those constraints or decide, gosh, I don't want to violate those constraints. I'd rather walk through one of these doors. Okay, so the 5 constraints are going to be roughly the classic von Neumann-Morgenstern axioms from expected utility theory, kind of adopted over to this history-based RL framework. So these come in the form of 4 axioms, and then we'll have a 5th at the end that I'll mention briefly. The first axiom we call the completeness axiom, which says that your preference relation has a genuine preference over every possible outcome. You can't abstain in any case. The second axiom is transitivity. So this rules out the case we just mentioned in terms of preferring these, this little circle of fruits. The third axiom is called independence. And roughly this means you can't mix together independent alternatives and somehow invert your preferences. We'll go into a little bit more detail on this one as well, because I think this is a particularly important one for us to reconsider in task specification, because this one will actually get rid of risk-sensitive objectives and things like constrained objectives. The fourth is called continuity, which just means there's always a way to break even between any 2 outcomes. And together, these 4 axioms comprise what are called the von Neumann and Morgenstern axioms, proposed by von Neumann and Morgenstern, and it's kind of landmark book, also from the 40s. And this closed a much earlier hypothesis called the expected utility hypothesis, proposed by Bernoulli in the 1700s. So these collectively tell us that maximizing expected utility is sort of the right thing to do if you satisfy these axioms, and these together will motivate history-based rewards. But we were particularly curious about Markov rewards, and it turns out in order to recover Markov rewards as the kind of correct thing, we need a 5th axiom, which we call temporal gamma indifference, which says roughly that the way you're discounting is consistent throughout time. There's more to say about that too. So I'll just give you a quick flavor of some of these axioms and kind of their basic structure to get a feel for what kinds of preferences they rule out. So we'll start with completeness. So this means you have a genuine preference between every outcome. So for instance, if you look at this tree of all possible histories, every point on that history tree, you have to have a preference between these 2 points. And in this sense, it's, I think, the most fraught axiom in many ways. Historically, there's quite a lot of work that argues against completeness, in part because the preference relation has to have an answer for kind of an infinite space of possibilities. So there's this really great paper by Aumann in the 60s that tries to reconstruct utility theory without the completeness axiom to some degree of success. And there's some kind of more philosophical arguments against the use of something like completeness that lean on these notions of incomparability or incommensurability, right? So in this paper, the author suggests, how can we compare violations of different virtues, like being honest as opposed to being just? These are just not 2 things that you can exchange between. Or similarly, how can you compare, eating an orange with a walk on the beach? They're just not comparable in any sense. And so there are just some experiences we shouldn't expect people to be able to trade off between. So the third axiom, independence, I mentioned that this throws away things like risk. The reason for that is if we have a preference, what this axiom means is if we have a preference over to an orange over an apple, it has to imply that if I give you a chance at getting an orange and the same chance of getting an apple, you have to prefer the chance of the orange. So the chance of getting something can't really change your preferences. And this is why risk-sensitive objectives are thrown out by the third axiom. So if we want to specify tasks that take into account riskiness or uncertainty, then we need to get rid of this third axiom. Okay, so with those 5 axioms, we can now state our main result, which is just that the conjecture I mentioned before is true, if and only if those 5 axioms are satisfied. So I want to highlight this if and only if, because this means anytime we write down a reward function, we're implicitly talking about a preference relation that satisfies the 5 axioms. So this is a huge requirement to place on the kinds of reward functions that we write down. Maybe intransitivity is an easy one to avoid, but I'd claim that some of these others, things like independence, are probably a little bit harder to ensure that we're capturing in the right way. And so as I think about the space of RLHF right now, and the fact that we're continuing to form reward models based on preference data, I think it's very likely that oftentimes the preference data we're collecting, these preference relations don't always satisfy these 5 axioms, which means we're assuming that the noise in the data should, or that any deviations from these axioms in the data should just be treated as noise. And that feels wrong. It feels like we're doing something wrong there. So this is the main result. Here are the 7 doors. The first 2 I mentioned are, how do we interpret the hypothesis? What does this hypothesis actually mean? And then these 5 axioms comprise the set of constraints on preferences we need in order for reward to sort of be the right thing to do in order to capture the goals that we care about. So I'll just highlight a few takeaways that I think are probably particularly important for thinking about task specification. So the first is, in a particular sense, the reward hypothesis is false. At the very least, there's nuance. So at the very least, there are choices of preference relations that we just can't write down in terms of a scalar reward function. Whether this means we should be thinking about multi-criteria objectives or deviations from the expectation, kind of up to us, whether or not these are actual limitations or not, but I think it's an important thing to highlight. So what this means is that there are choices of these goals that we cannot capture with a reward function in discount pair. So the second takeaway is that, as I mentioned, kind of people tend to not satisfy these axioms. So there's this really, I think, brilliant line of work from Kahneman and Tversky and Johnson and Laird in behavioral economics that shows people regularly deviate from the norms of rationality, which means, okay, thank you. Which means that if we're thinking about writing down reward functions based on our preferences, we need to be aware that our preferences don't necessarily satisfy these norms. As one example, if you're asked to choose your favorite shirt from amongst a collection and you're given a really big pool, Kahneman and Tversky had this nice experiment where they showed if you then ask the same participants to choose from a smaller pool, oftentimes preferences will invert. You'll end up preferring one shirt to another that you didn't when it was a bigger set of options. And this just speaks to the kind of complexity of human preferences, and that I think it really goes far beyond these traditional axioms of decision theory. So when we think about these 5 axioms, I think there's probably good reason to think that at the very least at the population level, we deviate from all 5 of these all the time. And so what I think that means is that when we write down reward functions, as I mentioned, we're kind of assuming that the preferences are rational. But really there's this space of, quote unquote, human preferences that maybe only have minimal surface area with this space of rational preferences. And as a result, I think it's probably important that when we specify tasks, we really kind of think more about the human at the center rather than the decision theory at the center. And we kind of make sure that we're incorporating the ways that humans prefer things and think about tasks into the way we write down our objectives. The third takeaway is that the deviation from independence in particular, I just want to emphasize again, I think this is one of the biggest opportunities for task specification, to think more about uncertainty, to think more about risk, to think about multi-criteria or constrained objectives. This feels like a big opportunity to really expand what's possible out there right now, to design algorithms for specifying these and learning algorithms and planning algorithms to account for these kinds of objectives. In the appendix of one of the papers I'll mention, we have an algorithm that is guaranteed to return the satisfying reward and discount pair, given this preference relation as input. The caveat is you need this preference relation to satisfy the 5 axioms, but this is actually an efficient algorithm to produce this reward discount pair. It's not really something that we can run right now because we have to assume the preference relation satisfies these axioms, but it's an area where I'm again excited about maybe basing approximations off of this algorithm. So the work I presented today is based really on a line of two papers. The first was from 2021, and then last year, this paper led by Mike Bowling and John Martin, and joint with Will Dabney, called Settling the Reward Hypothesis. This is really where most of the results I mentioned come from. So if you're curious, I encourage you to check out those papers. I want to extend a huge thank you to all my collaborators that have been involved with both of these projects. Really enjoyed working with everyone. It was a really fun group. And with that, I will close. Thank you so much.
Yeah, that was awesome. I'm still a little bit on the independence side. So, what do you mean by that? Let me ask this. So, should I, regardless of the probability of orange versus apple, I should always pick orange, and if the probability that is smaller, or what is it? What is it?
Right. Yeah. Good question. Yeah. Thank you. So the version of it that I like the most is that if you have the deterministic outcome, so you just are choosing between an orange and an apple, by telling me which of those you prefer, it also tells me how you prefer a chance of getting each of those things when the chance is the same. So if I give you a weighted coin and you tell me you like apples, or sorry, oranges more than apples, and then I give you a coin of any weight, you have to prefer the chance of getting the orange versus the chance of getting the apple. So the chance can't suddenly invert your preference. Say, well, if there's a chance I won't get my orange, then I want my apple instead. Right? That's the key. Yeah. Thanks, Hadas.
Discount factor because you had correlation.
Yeah.
And I wonder how much it's played out because focus a lot about the rewards and people that do machine learning usually focus about learning the reward. But is the discount factor is a very crucial part here?
Yeah, good question.
Is it very simple or like satisfied that you can only get
Great question. And let me just make sure I remember to repeat for the folks online. So the question is, I focused a lot on the rewards. Does the discount factor matter as much? How does it play out? Yeah, great question. Thank you. So I'll say that we adopted this perspective of discounts that depend on action and observation as a way to generalize from the traditional framing. So if you choose a constant discount factor, it could even be one, you could use average rewards, for instance, then that's a special case of this choice of discount factor. So we just wanted to make sure that if you do something else with your discount factor, as Martha White proposed in this earlier paper, that we can also account for how that plays out in the reward hypothesis. So it might be for some choices of preference relations, there are only kind of action observation conditional discount factors. You can't get away with a constant. So it does enrich the expressive power by moving to actions and observations. And we just want to make sure we're accounting for that as well.
So I agree, and I understand what you did, but just out of your experience, you have the algorithm to generate the reward and the discount factor. Does it usually is something natural, or it could be that I will get something very weird?
Yeah, good question. So
the theorem will be met, but only because I allowed this weird function to do something weird, and it's not the action that reward.
Yeah, interesting. I think the discounts probably are weird in some cases. Depends on how we want to think about weird, but typically we'll start with a utility function, and then you sort of unwrap what the stepwise rewards need to be, and then that points to what the discount factor has to be as well in order for the utility function to capture your preferences. So could be weird in some cases, that's how I summarize. Yeah, happy to talk more though. Thanks.
Say something quick, which is, this is a great talk, I really enjoyed it.
Thank you.
But you missed an opportunity
Mm.
because you're in the Netherlands.
Okay.
You didn't say anything about Dutch book.
Oh. Yeah. Good point. Yeah. Yeah, so Dutch booking is about an adversary kind of taking advantage of how you've chosen to prefer things, basically. Great point. If I get another chance, I will include a slide. Thank you.
Language and action.
actually to the world, where they study embodiment grounding of language and interaction. And we're very excited to have them be our next.
Thank you, Andy. I don't want to use that, no.
Okay.
If you can't hear me, then let me know. Otherwise, I'm planning to basically just roam around the room like a crazy person and yell a bit. Okay, I've not used this clicker before, so this will be interesting. That looks like a laser pointer. All right, cool. So, the title of this talk, do it like this and don't wake the baby. So, this is I want to kind of talk a little bit about sort of where I come from in terms of thinking about some of the problems. And then I'm mostly going to then use the rest of the half hour to advertise Vidhi, who's sitting right there. And so anything that is actually smart or like technical, she will answer. And I will just be up here and philosophize as I'm in my professor era. I like to sort of start off, but only if the clicker works. Okay, I like to start off thinking a little bit about sort of where I was when I started thinking about language grounding and embodiment. And for me, that largely is related to this work of Peter Anderson's. Now, obviously, language and robotics is much older than that. Stephanie Telix, for example, Joyce Chai being sort of the OGs of this space. But for me, once there was a simulator which had language in it, that allowed me to start sort of playing around and thinking a little bit about what it would mean for language to be the task specification for your robot to do something. Now, the thing to note is that these are reasonably explicit instructions. Peter is basically a computer vision guy. And so he was really thinking in terms of, to what extent can I embed each one of these phrases directly into something that would have a nice dot product with the vision? And he specifically collected the data set with that intention. So what we ended up doing a little bit later, come on, clicker. Okay, we may have to do it's fine. I'll do it like this. What we ended up doing a couple years later was trying to get sort of language instructions in a simulator. These were real images. These are simulated images where the instructions were a little bit higher level. So put a gray bowl with a watch in it. And the idea was that when you think about language, when you think about specifying a task, there's a lot of stuff that is not specified. This, I think, at this point is pretty well known to everybody. You're like, yeah, of course. I don't spell out everything in minute detail. I give some notion of maybe a goal, and then I assume that the agent's going to be able to infer backwards from that. And it's quite difficult in general to get a robot to do anything. So, for example, when we try to get the systems, the robots actually do stuff in the real world, we simplify these instructions even further. So in this case, if you're going to go do a pick and place task, then that decomposes into binding and so forth. So it's a similar kind of idea to what's above, which is that I have some sort of a goal. It's somewhat underspecified, but it's underspecified in the sense that it doesn't give you all of the low-level actions that you need to execute. So normally what I do when I think about this space is I think in terms of, now the clicker works. I clicked the wrong button. I think about this in terms of sort of the complexity that we have along 3 different dimensions of grounding. So here I have language as one dimension. I have vision as the second, so we'll start there. I'll put some random data sets up, which have maybe increasing amounts of sort of realism as I move along the axes. And then obviously we care a lot about this third axis, which is action, where we can then put some of this work down on this axis as well. And so here we have cobots and things like this historically. And so we can ask questions like, how does a richer action space break our algorithms, like our language understanding algorithms? That might look like, how is it that our systems are able to handle or not handle, needing more memory, increasing the difficulty of doing alignment, recognizing, as per the previous slide, pre and post conditions in order to execute some sort of a task. We might think about like how the output space not being discrete might make our task more difficult. So how do we deal with end effector position, things like this. And then the other dimension, which I'm maybe a little more unique on in terms of this community, is the sort of language complexity and how that relates to things like theory of mind, or when we use language and what do we mean by language. So that may mean things like the complexity of our interlocutor. So how many people am I interacting with? What prior knowledge do each of them have? And I'm particularly interested in how all of these change or inform language. So we're kind of up here. This is kind of where we want to be, sort of in this kind of realism in every dimension possible. But what I'm going to now do is that instead of going into any of those, I'm going to ask this question, which is like, what specifically is not specified in those instructions, so in those tasks. So the rest of this talk is basically just saying, you know this, you know these are all hard, you know you need to think about these things. Let's talk about what's not actually written down and what kind of inferences we're expecting our models to make or not. So how many people here are familiar with Grice's maxims? Oh, we have a couple. Great. So the Grice's maxims, which we can get into a philosophical argument later about whether or not we agree with them. This is specifically the cooperative principle. This is one of the original quotes. If you go and pull from Wikipedia, it basically says that whenever you are giving information to another person, whenever you're speaking with someone, you're collaborating with that person, you are going to give whatever information is required, is necessary to do that, and sort of nothing else. So you're going to be informative, you're going to be truthful, you're going to be relevant, you're going to be clear. These are sort of the four slight simplifications of the four maxims. And so now, if we think about this in the context of a task specification, that means that I'm going to give you a task specification that is clearly indicating what I want, except that the clearest way for me to make it clear, the clearest way to make whatever, is to give you an entire paragraph of text that describes every possible thing. And I'm not going to do that because I'm going to only say what's relevant. And but I want to make sure that what I'm saying is still informative. And in order to do this, I need to understand everything about sort of where you're coming from. So what isn't said? That's basically the punchline. So I'm going to talk about two things. I'm not going to go into, I'm going to talk a little bit about, if you were at Vivi's poster on Vid to Robot, she covered all the technical stuff. So I'm going to do the annoying analysis part. And then I'm going to talk about some work that we have that it sort of moves past that into sort of the audio space. And I'm going to view them from this question, these corresponding questions. What is implied by a demonstration and what is implied by embodiment? And I'll explain what I mean by both of those more in a second. Okay, so the idea behind the Vid to Robot work is that you have a robot that's observing a human doing a task, and then you want your model to be able to complete the task as shown. We've all, understand the premise. We've all wanted to train robots to do stuff before. So here the human is putting something in the bottom drawer, and the robot needs to do the same. And then in order to do this, how do you actually make that possible? Well, you collect a ton of videos, you have a ton of line data where you are performing various tasks around the environment, and then you are hoping that your system is able to generalize from those, is able to pull something from that. The basic architecture, which I'm going to sort of skim past at 1,000,000 miles an hour, being that I have to obviously have some representation of what I'm observing. I have to have some representation of state. I have to be able to then use that in order to actually predict actions. Okay, there's a lot of smarts here. She's here. She will address the smart bits. What I want to do is say, if I have this paradigm, I am maneuvering an object. And I think for most of us, because we have the prior, which is, oh, I'm trying to train a robot to do a manipulation task or something like this, we are going to look at these scenes with a certain lens, so a certain sort of view on them. And we're going to end up ignoring a lot of interesting questions about what is actually the content of the demonstration versus what we're just assuming it's supposed to infer. So let me do this. You showed me what to do, so now I'll do it. But the question is what was shown and what was implied. Here is a simple example. So open the middle drawer. We have some prompt video. Oops, sorry. Try that again. Hold on. I think it will just play. It won't play. Okay, there it goes. No. All right, fine. You have we'll do it one more time. It started playing. I'm not touching anything. Nothing's happening. Do I click a button? Vote from the crowd? Yes, we click a button. Okay, it's fine. So, okay, so here we have a bunch of demonstrations, some of them successful, some of them unsuccessful, and that's fine. So we have our demonstration on the left, which is we have this teleoping, let's say a robot that's taking this can of Coke and writing it. And then on the right, we have a ton of other objects that could also be writed, that this could be generalized to. So here's the question. That's my final condition. This is what I've just presented. That's my demonstration. and I have some target objects like this. What is the correct way for me to generalize the orientation of the can of LaCroix or whatever to a cup? So let's do the obvious. Is it like this, or is it like this? Okay, how many of you store your cups in your cabinet like this versus like that? Okay, so how many people put them upright? How many people put them upside down? Great. So, should I take from this that when I move over to this, that I want this vertical axis and I don't care about the up and down? Should I take from this that, oh, well, the opening is here and it must imply that I want this to be oriented in this way? Like, we don't have an answer to that question. And it's only going to get worse when I throw a stapler in here. What is the correct way for me to transfer orienting a can of LaCroix to the stapler? So what the robot's actually going to do, which was on the previous slide, or I think we'll show in a second, is it's going to turn it upwards. But you can see what's actually happening here is that if I give you the context, which is that if I had not asked this question, if I had not primed you, and I had simply given you these 4 objects, you would have said, oh, all of these are longer in one axis than another, or they're like semi-cylindrical if you kind of look at them the right way. And so like what's supposed to be happening is it's supposed to be inferring that there's a primary axis, and then I want you to do the movement along that axis. And so you would get really excited that it did this nonsensical thing with a stapler. So it's not wrong, it's just that it's not right. And I think that's like the thing that I basically want you to take away from this, which is that when you're doing these things, you have some intention about like what you're looking for. And when you don't have a complete task spec, there's no way for the model to know that that's what your goal is. And that's okay, because that's the same thing with humans. So it is not the case that as a human, you would have given a complete task spec. It's just that as a human, you would have had some additional context, like for example, in this case, 4 other objects that are all being oriented along that same axis. And so therefore, you would infer that what was intended was the following generalization. So let me give you a slightly more, I think, realistic scenario you might be in. So here we have a prompt video, which is closing the middle drawer. The robot shows up and the top drawer is open. Is it correct for the robot to close the top drawer? Or should the robot show up, see that the middle drawer is already closed and be like, oh, we're all good here? Right, there's no answer. That's going to be the whole theme here. So like there's, at a certain point, I'll just stop asking the question. But I really, really like this. I both really like it because I like the work and I like the fact that it is actually performing sort of reasonable actions in the world. But I also really like that it's such a beautiful demonstration of these issues that we run into. I think I'll do one last one. So here we have a demonstration video on the left, where the robot is going to go put the chips bag into this top drawer. And then on the right, we have 2 objects. So we have this RX bar and we have this apple. And so now it needs to perform the same task with both of those, which it should start doing now. Okay, which object should put it in the drawer? Which object? Okay, we have a vote for both. Anyone else, quick? Which one? Just either one, as long as it's one of them. No, okay, good. So it's going to go for the RX bar. And I think once you've seen that, you can make a counterfactual argument that was the right thing to do. And be like, ah, yes, it's the packaged food. Of course, to put packaged food in the drawer, you wouldn't put the fresh fruit in the drawer. Doesn't make any sense. We've achieved AGI in the form of food. Okay, so the actual process for creating this data, as I said, there's like she collects, gets all of this data together so that we can do this. So that you have a bunch of these prompt videos where you have things that are distractors in the environment. Then you have the robot video where you have different distractor objects that are going to, that it has to actually do inference on. And so in this case, recognizing that the key items here are this green bag of chips, and then moving it next to the Coke can, and so not getting distracted by the other. And so we can do this for a whole series of these types of actions. So again, closing the middle drawer here, and then having that alignment. And I'm gonna, just for the sake of time, skip ahead a little bit and be like, there's a lot of these. So picking up all these, but every single one of them, when we look at the actual text, is by definition going to be underspecified. And I think there's also sort of something interesting about if you then were to look at the data distribution for training with transferring from a robot versus doing sort of a hindsight annotation kind of setup where you take the trajectory and then you label the goal versus having a human do something and then transferring it. Because again, I think that whenever we're in the mindset of the robot, we're going to sort of think about kind of these canonical atomic things that we're building from. And when we're just performing a task ourselves, we might not be doing that. So sorry for the black to white transition. So the what is state, what is assumed, what is the intent are all sort of underspecified parts of that. So that is the simplest case and sort of the first part of this talk, which is I thought I was just telling the robot how to do something. I thought it was totally obvious to the robot what I wanted to do, but I don't have common ground with the robot. I don't have theory of mind with the robot. So there's no reason that it should interpret these things the way that I did. And so therefore it's unclear what the actual task specification was. The second thing that I wanted to sort of put in your head as like a thing that we've been thinking about is the fact that when you are an embodied agent in space, you take up space, you make noise, you exist. And so there's a similar question here, which is if I ask you to do something, what am I not saying because I am assuming that you understand it? So in this work, the idea is that if you have a robot that's in this space and you ask it to just do a simple navigation task, for example, in the environment, did you, as part of that, assume it was not going to do X, Y, or Z? So what did you assume? You assumed it was probably not going to run over the cat. You assumed it was probably not going to knock over a whole bunch of objects. But did you also assume that it was going to be maybe aware of the fact that this robot's quiet and this one is not? So if I was asleep in the other room, for example, is it supposed to be conditioning on that information? Is it supposed to be aware of that? And it's a thing which, again, if I was talking to a human, I would not say. If it was clear that I had just put the baby to sleep, I would really prefer that the person not run through the house banging pots and pans, or that they not slam doors, or they not do all the other kinds of things. They're not technically part of the task specification, but they are socially part of the task specification. And so therefore, they are important. So the question we wanted to ask here was, can we start to kind of look at what the challenges are for bridging that gap? So it's instead of just assuming that I have this world with no other people in it or there's no other consequences, can I start to think a little bit about that challenge? And what we don't fully address, but I just want to put in your head is that robots are not a single sound, right? So if the robot is running, it's much louder than when it's walking. Even with our quieter robot friend, when he's turning versus when he's going straight, he's going to make very different sounds. Now, if you've never worked with sound before, which is fine because a lot of us haven't, you might be familiar with this notion that it has a decay, right? So as I get further away, things get quieter. That seems to make sense. You took physics in high school, and they said something about moving air, bouncing into itself or something like this. And so if I gave you a room like this, and I said, like you're standing here and you're projecting out, you would basically draw correctly something that kind of looks like this, which is sort of like if I was producing a sound at a certain decibel, like here's how it's going to decay as it moves away from me. Similarly, though, if you were in a room like this, so if you were in GHC standing outside of our lab at CMU, then you would notice that there was this pane here, there's these stairs here, and you would start to have this slightly more complicated, you do it intuitively, but a slightly more complicated notion of the space, which is that there might be some amount of echoing over here, but some sound blocking that would happen if you were in front of it. If there's a student here that doesn't want to be disturbed, you would then sort of navigate in those other paths. And this is what the actual model starts to predict, which is that you do have these, most of us don't think in 360, so I realize it's like a little counterintuitive to look at. But this notion that like actually the sound is right in front of me. So a simple way that you could try to approach this problem is that you could basically say, here's a 360 view of the environment. I have some listener somewhere. The baby is 9.6 meters in that direction. To what extent can I encode all that information and then predict how loud they would perceive me? And as was just implied on the previous slide, that's an incredibly complex nonlinear function. So it's a function of the architecture of the room that you're in. It's a function of the materials in the room that you're in, all of these other kinds of things. And so if we start to plot that, you end up with this crazy sort of distribution over the sound that's being received at these various distances from you. And here's your simple decay, here's your best fit, and here is what the model is trained to predict. Now, I think we can all look at that and be like, well, clearly it's amazing. What a wonderful model. There's red on top of blue. It's really hard to actually evaluate this because there's so many nonlinearities in this space because of all these properties, and there's so much that's unknown that what we're looking for here is basically sort of a distribution match. So we can at least see that there's more of that distribution match over here. We can see how things that are maybe within line of sight are getting a very different property versus those that are not, things like this. But the most basic takeaway from all of that is that if I then was to record the audio of the student who's sitting right here, when I have a robot that goes around the back versus was to go past them, then I will get very different sound profiles for that person. These are the actual recordings, and I know all of you love looking at these plots. So to help you, there's this lot of red here. So this is because we're not going to see an appreciable difference in the perceived sound at the beginning of this trajectory. We're talking small, sort of 1 meter, less than a meter sort of changes. So where things are going to differ is that once we get behind this versus we start moving towards the person and they get louder. And so the goal here is that if we can build systems that actually have this kind of understanding, this ability to do this kind of modeling, then we can go back to our original goal. We can be like, okay, wait a second. What is navigation? Oh, wait, navigation is this contextual, like that task specification is contextual awareness of what our the environment is. Those were things that were not specified because they were assumed under sort of Grice's maxims that we would just understand that you don't want to wake up the baby, for example. And so therefore, our planner should be including all kinds of costs that come from basically the consequences of our actions in the environment. Okay, so when we therefore think about sort of our task specifications and stuff like this, we end up with these sorts of questions that I want to leave you with. I like leaving you with questions and basically no answers. Here, there were 2 papers where they were, or pieces of work, and they're both great, and neither of them solves the problem because there's these underlying issues of what's stated, what was pragmatically understood when you were giving these utterances, what knowledge was assumed, even back in the original case, knowledge maybe about the canonical orientation of objects, things like this. And then what modalities are used. So if we're impressed with ourselves because we have good world models and understand the physics and the consequences of if the robot was to run into something, but we aren't including, for example, the audio space, which a lot of us also experience, then we have a simplified and sort of impoverished version of what the actual goal and task specification was. And so with that, thank you. She's right there. I know she's embarrassed by it, but she'll be able to answer everything you could ever want. Thank you.
Rob Yonatan, 4 minutes to begin, so we'll give him 2 minutes if anyone wants to begin.
Yeah, hit me.
I don't know exactly how to phrase this question.
Best questions. Thank you.
Great talk. I loved it. I really buy the vision, but I also wonder, your slides have text descriptions of things that you're looking for. And Bit2Robot is demonstrating these capabilities that are simple prompts, but if we make them more complex in order to capture some of these things that you would like to be either invariant to or conditioned on.
Yes, so we maybe should. I don't want to. What I think I would like to do instead is come at this from maybe more like a continual learning paradigm or something like this, and think about what it would mean to compress all of that context when we then give that next demonstration. And so I think my ideal situation is that we don't actually make the prompts more complicated. We don't actually bake more in there, but we have models that have a better understanding of context. Yeah. Go for it.
So, better understanding of context. Do you think it's realistic to have a model that has context that works for someone for life for people? Or how do you break it down? Just like, we can't get to know.
We have 3 to 5 years for AGI, right? So like, I think it's right. Yeah. So I think that this is not operational. We were having this discussion a little bit right before the talk actually. I think one of the key things that's missing okay, I want to be careful. Continual learning is a pretty broad field with a lot of great stuff in it. But at a very quick, high level soundbite level, I think forgetting is not emphasized enough. And so I think that the idea is that, so yes, if the naive way that we see this happening a lot right now is that we basically just, have this growing prompt context window or something like this. And like, oh, well, now I have 1 million tokens with whatever else. I'll just keep putting, so I don't like that. But the notion that you should be you should basically be going to sleep every night. You should be distilling sort of some key sort of summary of what those experiences are, what things did or didn't change, what things are common, and then building sort of an updated representation that you use as your context for that environment for that person the next day, I think is a sort of more tractable proposal. Now, doing that cross-modally is still not easy.
But is it something that you can perceive one robot, one context, particularly building that context? Do you see that something broader that can be transferred to? Are there some basic principles that?
Yeah, I'm somewhat inclined against the notion of one robot that does all. Insofar as that, at least personally, if you put me in an operating room, don't do that. I wouldn't have any idea what to do, right? And I think that that's okay. In fact, more realistically, even if I was visiting somebody in like a hospital setting, I don't even know the basic social protocols for that space. And so then I end up sort of falling back to sort of really, really basic policies, right? Of like sort of looking for a front desk and asking all these other kinds of things, and not even assuming that the numbers maybe go up chronologically. And so I actually would probably prefer systems that had that humility than ones that are sort of designed to somehow do this kind of transfer across everything. But yeah, okay, sorry, I will get out of your way.
And as designed, here to talk about continual learning is my lab mate, Cédric. So Cédric is a postdoc at MIT working with Josh Campbell and Jacob Andres. He previously completed his PhD at INREA, where he worked on recommended accelerator. And so we're excited to hear all about this.
Cool, thank you. I don't really know how to use a mic, so if at some point I turn my face and you don't hear me anymore, just tell me. All right. Hi, yeah. So it feels like today's main question is basically how should we ask robots to do stuff? And of course, I'm going to say a word about that, but I think that I want to take a slightly complementary perspective and defend that general purpose robots should not only pursue our goals, but that they should also learn to represent and pursue their own goals, so that it should be autotelic. And hopefully, as they do their own self-directed exploration of the world, they will also get better at achieving our goals too. Okay, so the first question is why should we have robots that achieve their own goals? And I'm going to offer two different motivations for that. The first one is going to be more scientific, and the second one more practical. The first one is that I'm interested in modeling the open-ended developments and learning trajectories of humans. And we know from developmental psychology that human skill acquisition and learning is really developmental in the sense that we build over the skills that we've already acquired to learn new skills. And it's also very self-directed. We seem to know what to learn, when to learn it, from whom to learn it. And we kind of get out there, go gather the data and the practice that we need to achieve our learning goals. So in childhood, this follows some like relatively predictable sequence of pseudo stages. But after that, we start representing our own goals and pushing our own goals. And this is where the trajectories of humans really diverge. And so I'm interested in uncovering kind of the fundamental mechanisms that underlie this open-ended learning. And it connects to this definition of intelligence by McCarthy, who coined the term AI, when he said that intelligence is the computational part of the ability to achieve goals in the world. I got that from your paper. And I think it's true that as you're able to represent more diverse and more complex goals, you kind of gain more agency and more control over your environments. And so you gain more capacity for adaptation. And if you're beyond that, also able to imagine your own goals, like beyond the one that nature gave you, then you get better at, you're more creative, you get better at innovation, and also better at just exploring the space of all possible behaviors. And all of those are very key elements of ecological success for humans. The second reason is more practical, is that we might want to build general purpose robots. And so that means that we need to generalize to a huge diversity of goals and adapt to a huge diversity of domains. And the robots that we have for now, they maybe do a few tasks in a few domains. And there's like this idea that maybe you could just pre-train a robot in a factory and hopefully they just deploy it, then deploy a static robot and hope they will generalize to all those goals and domains. I think that's probably not true. And if you want to really be able to adapt to all those goals and domains, it's not only that it's a big space, it's also that you have a huge uncertainty about which goals and domains the robot will face. So if you want that, you need robots that continuously and autonomously learn. And that will mean that they will have to generate their own learning signals, their own reward functions, build their own curriculum towards the hardest goals and so on. And so they will need to be autotelic. So taking a step back, what does it mean for a robot to have a goal? In psychology, people talk about a goal as a cognitive representation of a future object that the organism is going to commit to approach or to avoid. And so we can translate that into machine learning terms, maybe some reward function that measures progress or achievement of the goal, and some goal embedding, which is like the cognitive representation here that points towards the goal. So you can condition your policy on this goal embedding and then use the reward function as feedback. And I'm making an underlying assumption here, which is the reward hypothesis. I'm not going to talk much more about that. It was presented earlier. I'm just going to assume that for a large set of goals, it's holding, and so we can roll with that. And so people have considered a diversity of such goal representations. Sometimes it's just like a point in observation space. Sometimes it's maybe a set of binary predicates that you want to be true. Sometimes it's a linguistic statement that you want to be true about the world. So all of those different goals, and they are also expressed in a diversity of modalities. Can be more visual, auditory, or more abstract, linguistics, and so on. And so far, I don't think it's clear that there will be like a single goal representation that can kind of encompass all that diversity of things that we call goals, or whether we're going to have like goal modules, basically, that will be able to communicate to each other. So now about this autotelic term, it comes from the Greek auto, which means self, and telos, which means the end or the goal. And so it's simply an agent that is intrinsically motivated to learn to represent, generate, pursue, and master their own goals. So if you compare it to a standard reinforcement learning agent that acts, receives states, and that receives its goals and rewards from some external source, usually an engineer, here the agent has to generate their own goals and rewards. And this is how they get really autonomous. And as they interact with the world, they will kind of grow along their life a repertoire of skills, which are just a set of goal representations and the associated goal-directed behavior. And I guess one objective here could be that this process of skill accumulation becomes kind of autocatalytic or open-ended, we could say, in the sense that the more skills you have, and the better you're going to get at reaching more diverse and more complex goals. All right, so now I'm going to go over like a couple of ingredients that we need to build such autotelic agents. The first one is that we need agents that can practice many skills in parallel and can learn to trust very efficiently across them. So we can maybe do that by having like goal condition neural policies that will share representations across goals within the network. We can combine that with a form of inside experience replay, which is basically a counterfactual learning approach that tries to squeeze as much information as possible from every trajectory. And the combination of that and so those two give more transfer and so more faster learning, hopefully. And so we can look at that in a robotic manipulation domain where we bundle together 4 different types of goal manipulations. So you have like a reaching task, pushing blocks, pick and place blocks, and stacking blocks. And there we train a single agent, a single policy to achieve all of those goals in parallel. Also doing like some counterfactual learning across those goal representations. And that's the blue line here. We see that it learns basically much faster than if you were to train independent policies in each of those goal types without any kind of communication. So the bottom line here is that as you represent more goals, you have more possibility for transfers across them. And you also like kind of shape the reward towards, because there are easy goals that you can achieve now and train your representation on. You also get better at exploration, basically. The second ingredient is that you need to let agents select their own goals. If you think of really large representation of goal spaces, they're going to be full of goals that are completely impossible for the agents. Maybe because they are like physically impossible, maybe because the agent is not that good enough for now. Also full of like trivial goals. And you have only like one limited lifetime. So you need to decide to prioritize what to practice at any given point. So you can see that as an optimization problem, where the goal is to optimize for an optimal, find the optimal goal selection policy that will maximize your kind of expected performance over all possible goals that you might care about, like extrinsic goals maybe. And this over the whole lifetime of the agent. So if you do any kind of optimization, you realize that it's a really hard optimization problem because you get only one feedback per life. So you need some kind of outer loop evolutionary meta-learning process to optimize for that. But what researchers came up with, it's also what natural evolution came up with, is the idea of using more proximal objectives that are can be optimized by the agent during its lifetime, and that hopefully will correlate well with the two objectives. And in practice, these take the form of intrinsic motivations. You can have agents that focus on goals where that have intermediate difficulty, or goals that are more novel, goals where they progress the most. And the commonality between those is that the intrinsic motivations are constantly redefined as a function of the agent's current experience, or current capabilities, let's say. And so it's going to like shift the objective of what the goals, which goals the agent focus on, and organize, drive basically the learning trajectory of the agent. We can go back to the robotic domain. Here we gave it an intrinsic motivation towards learning progress. And so for that, the agent needs to have some kind of self-knowledge. So in practice, we're going to have it track its own competence. So it's kind of average success rate in each of the goal types. It's going to track also the learning progress, which are derivative of those curves. So learning progress or competence progress. And then it's going to use a kind of Bennett algorithm to sample goals that are preferentially that have the highest learning progress. So we can see how that plays out. It makes progress on the easiest reaching task. Learning progress increases. The interest of the agent increases. It starts sampling them more. And so quickly it reaches mastery there. Learning progress is going to drop. Interest is going to drop. And it's going to start focusing on a second task where it's making progress, which is here the pushing task. So you can see how that plays out. Basically, the agent is going to like shift its focus from simpler to harder tasks as it learns. And this is going to organize some kind of curriculum automatically for the agent. So if you take a step back here, for now, we had like the goal condition agents that has goals that we give to them, some goal representations and reward functions that we also give. We give everything. It's just a normal reinforcement learning agent. The curriculum learning variant is just learning to sample those goal space, but it still relies on some hand-coded representations of goals and rewards. But you can see already how like playing this kind of agent in a large goal space, and if you like give a lot of compute to the agent, such as it can achieve some of those goals, you can already have like some really developmental trajectory and manages to reach really high, really difficult goals. And we've seen that in like a couple of different approaches in POET, for example, from Uber AI Labs, Ada from DeepMind, and so on. But it's still like you're still going to be only able to represent goals that are kind of bounded by the first goal representations that you gave to the agents. And if you want something really open-ended, you're going to need the third ingredient, which is to constantly evolve the goal representations and the associated reward functions. So now we're going to go over like a couple of ideas of how this could be implemented in practice. The first one is that we can reuse unsupervised learning mechanisms, methods that learn like state or trajectory representations. And once you have those, you can basically use them as goal representations. So people have done that usually in the context of visual observations, where it's too hard to just set a point in visual space because it's too high dimensional and unstructured. So you can't really like set a goal there. But what you can do is to use the visual data you collect here, those points, to fit a generative model, maybe a VAE. And once you have that, you can consider the latent space to be your goal representations. So now you can sample the goal in latent space, you can decode it into a target image that you want to achieve, maybe. The problem with that is that you're only fitting your current experience, your past experience. And so the goals that you're going to sample are also going to be within the type of things that you already experienced. It's not going to really drive your exploration. It's not going to ask you to do anything new. So one thing that you can do that's pretty simple is just to upsample the observations that are in low density areas. And in practice, when you train a generative model, it's just going to give it some bias towards novelty, to focus on like generating goals that are a bit novel, a bit different from everything else. And so in this approach, there is all the ingredients. You have like a constantly evolving goal representations thanks to the autoencoder. You also have new reward functions here. I didn't mention that yet, but the reward here is like the similarity between your latent goal, which is in latent space, and the latent embedding of your current state. So you can get some distance measure there. And you also always evolving the way you sample because it's the novelty intrinsic motivation here. All right. A second thing that you can do is to use social feedback, to use social learning. And I think goal representations, if you need to evolve goal representations within an agent, you need some social feedback such that they become more aligned with what people represent as goals. So in this set of experiments, the imaging agent here is helped by some kind of social partner here, simulated one that's describes in a simple language whenever the agent does something interesting. So whenever maybe it goes somewhere, maybe it grasps an object or it feeds an object with supplies, like food or water. It receives a description of that. And so in the first phase, the job of the agent is to internalize those representations to make it their own goal representations. So the first thing that you can do is just store the descriptions that you've heard and the trajectory that are associated with that. And then you can later on just resample those descriptions and use them as goals, maybe. The second thing, a bit more interesting, is that you can learn a reward function from those. You can learn kind of a binary classifier that learns to recognize whenever a description describes well a trajectory. Once you have those goal representations, then you can move on to a second phase, which is more exploratory. Here, the social partner is not there anymore. And we gave it some kind of symbolic generative model that would like take the description that it has heard and kind of recombine them in different ways. And the way you do that, then, I mean, when you do that, you kind of get some new goals, so imagined goals in that case. And now we can condition the policy on those goals and let the agents go explore condition on those goals. But more interestingly, what you can do is that you can rely on the generalization capabilities of the reward function. So instead of just following the goals and trying to achieve them, you can also compute rewards towards them and then kind of train autonomously towards them. So now exploration is not only about adding some noise on the policy or maybe optimizing for some perceptual novelty. Now exploration is about imagining your own goals and then actually committing to them, going in the world, explore towards them and training towards them. So here it's a pretty simple environment. So imagine only simple goals. Imagine that you can feed plants. That was never said by the social partner. You can try to do that. You can get better at doing that also with its own learning signals. And then he imagines they could feed furniture as well. And in that case, it doesn't work. You cannot really like feed a door with Apple. But I would argue that when you look at the agent doing that and exploring in this way, you still kind of endow it with some form of agency. It still looks like it's committing to something and trying to achieve something. And it's a much more like structured exploration mechanism, I would say. And that's because the goal that it imagines and pursues is kind of expressed in the same language that we express our own goals. And so it looks more human in that way. Okay, now a third idea. So in the previous one, we used the language to represent more abstract and time-extended goals. And so we can push that and say, maybe we can reuse the pre-trained representations of large language models as goal representations and kind of leverage their ability and then sense of common sense to guide the sampling of goals. Because the one limitation of intrinsic motivations alone is that if you imagine that anything could be a goal, right? You're in the real world, anything could be a goal. Then there's kind of an infinite amount of goals that would be novel, infinite amount of goals where you could be making progress. So you need some other way to further constrain the goal generation. And here humans have like other constraints. So we would have goals that use objects that are around, so that are more like context sensitive. We would set up goals that respects the laws of physics, that respect social norms, that would be like plausibly useful for later achievements that we want to have. So we need to like embed this kind of common sense and human intuitive notion of what's interesting and relevant, in addition with the intrinsic motivations to guide the goal selection. So we looked at whether we could do that with language models. It was one project led by collaborators at Berkeley, and one in collaboration with people at INRIA and Microsoft. So in this one, we have like a 2D version of Minecraft that's called Crafter. We can turn the states into language, and then we can ask the language model, what should I do next? We see a bunch of goals here. The interesting things to note are that they are kind of diverse, not the same twice. They respect physics. You would like eat a cow or cut down the tree. You would never like build a cow or drink a tree or this kind of weird stuff that other models could invent. And they're also context sensitive in the sense that they suggest goals that are relevant to the actual current state of the agent and the current inventory. So it's a way of like incorporating some kind of loose common sense in the goal generation. And once you have that, you can like further prompt the language models to also integrate some form of intrinsic motivations. So what you need to do basically, I mean, the assumption here is that language models have these universal representations where potentially any kind of goals could be expressed. So your job is to like provide the right context to the language model such that you focus it on giving the right kind of goals for the agent. So it's already what we've been doing here by providing the immediate like state context to the agent such that it would give like context sensitive elements. But for intrinsic motivation, you need to provide some self-knowledge context to the language model as well. You need to tell the language model which kind of goals you've already experienced, which ones you find currently too difficult, which one you master already, which one you're making progress on, and so on. And if you give this right context, then the language model can shift its recommendations, integrating both the common sense and the intrinsic motivations. One last thing that I didn't mention here is that I've talked about how to generate goal descriptions. But as I've said, the goal representations are not only the embeddings or the description, but also the reward function. So you also need that. You can get that in various ways. One way is like if you can rely on a captioner, then you can kind of measure the similarity between your goal description and the caption of your trajectory, something like that. Or maybe get the likelihood of the goal under the captioner, something like that. And that works pretty well, but you need a good captioner, which is very hard to get. Another thing that you can do is just ask the language model. So you feed the whole trajectory to the model. Maybe it's text, maybe it's like a video, and you need to use like some multimodal model. And you ask whether the goal was reached. It's going to be good in some ways and bad in others, as often. But the interesting thing is that from that, you can also get other outcomes that were achieved in the trajectory. You can ask, so did I achieve the goal? And also, what else did I do? And once you get those labels of other things that you could do, you had achieved, then you can use them basically to do some kind of inside experience replay. So you can learn also more broadly, not only about your current goals, but about other goals. And the last idea is that you can ask the language model to convert those goal description into a Python-based reward function that you can just run on the trajectory at the end. And the good thing is that it makes it much more interpretable. You can look at the code, you can see if there's, you can debug it more easily and so on. All right, so the takeaways here are that general purpose robots must generate their own learning signals if they want to adapt to any kind of goals and domains that they might have to face. And so for that, they're going to need to be autotelic. That autotelic learning is basically made of 3 ingredients, maybe more. The first one is that they need to achieve many skills in parallel and efficiently transfer across them. The second is that they need intrinsic motivation to kind of drive the selection of goals within huge goal spaces and prioritize. And the third one is that they need to also continuously evolve their goal representations as a function of their experience. And so you can get that from unsupervised learning processes. You need also to incorporate some social feedback to align the goal spaces across agents and between agents and humans. And in this idea is also the fact that you can't just rely on intrinsic motivations. You need to integrate also forms of common sense in your goal setting. All right, the last point is that we still haven't built any kind of truly open-ended system. If we define open-endedness as the endless generation of novel and interesting artifacts, where artifacts can be like robot skills, but also be like artificial creatures or like arts or program problems or something like that, anything basically. And so we have a lot of interesting diversity producing algorithms. There are like the quality diversity side, the autotelic approach that I presented today, but they all converge pretty fast. Like after maybe a day or like maybe a week, up to a week maybe, they kind of run out of new things that it could generate, like new robot skills or like more complex robot skills. They converge. And so, yeah, to take back this bit from Ken Stanley, it seems that we still haven't found like the necessary and sufficient condition that would like kickstart the open-ended process, because then it would mean that we could run it kind of forever. It would still like continually present new interesting artifacts. And so natural evolution has been running for forever, basically, and still like not plateauing. It's still like generating new interesting things. So we still haven't found those necessary conditions, and there is like much more work to be done. I don't know if I have time to go over these different questions, but they are like the open questions for me. There are many more, I'm sure. So what makes a good goal, an interesting goal, a game fun? So what are like the real interesting motivations behind that? The one I'm especially excited about is like, how do we combine this autotelic learning with ideas from cultural evolution? So how do you evolve goal representations, not only in a way that lets you interact, achieve some goals, so not in an intrinsically motivated direction, but also in kind of as a population where like your goal representations are influenced by the one of others, and now yours also influences others. All right, last thing I want to say is that if you're interested in these kind of questions, you should consider joining the intrinsically motivated open-ended learning community, which organizes events and discussions around those questions. We have a workshop at NeurIPS later this year. And yeah, I want to thank all my collaborators on the projects and ideas that are presented today. And I'd like to thank you for your attention. Thank you.
Thank you, Cédric. And we have some, we started late on this one, so we have some time for questions. I was curious about this representation. Different representations make the same will have different group, but also for us as designers. I was curious what you think about the representation, right? more aspect of the problems and design, actually understand.
Yeah. Thanks. Good question. Yeah, so I think, I think about that problem as you need kind of the reward function, the unambiguous thing that defines what the robot is trying to achieve. And then the goal representation is more to like help the robots relate that goal to other goals that it has seen, or like decompose it into sub goals. So it's like giving cues of how to achieve that goal that you wouldn't get from like, let's say, a neural reward functions that doesn't give you any information, right? So it's more like like kind of cues to like learn how to achieve the goal. And I think the second part of the question is like, how does that relate to how people ask a robot what to do something? Sorry. And so I think of that as like, they are in a representation of what are goals within the robot, and the designer or the person instructing it doesn't need to know that and shouldn't have to know that because it's very complicated probably. So instead, what other people, when you instruct, you would like describe, you would give a demonstration, you would give an example maybe. And the job of the robot is kind of to do inference over that. It's like, what would be the goal that they would have in their minds that would lead them to generate those cues to me? And then you need to do this kind of Bayesian inference of like, so what is the goal representation that I should represent for that goal? And I think, yeah, that's how we solve like the communication thing, I think.
Any other questions? Maybe I'll ask one. So coming from a robotics background, I was wondering, Yonatan work, how do we extend to like on the real robots, where the action space of and the observation space are more complex?
Yeah. Yeah, there are two components. There is like, I'm mostly interested in how you represent goals, but then obviously if you want to have these like co-evolution of goal representations and goal like behaviors, goal-related behaviors, you also need like the goal-related behaviors to like catch up, right? You can't just be imagining goals and then have the agent do nothing. So yeah, I guess nowadays like it's easier to imagine goals than to reach them. So we need to make kind of progress on that dimension. And the other thing that I want to say is that there's this like vision from, I've heard George Konidaris talk about that a lot, that if you want to be like truly general purpose, you need to have very low level sensors, very low level representations, because for some tasks you might have to like do really fine things. But if you want to solve very like abstract problems, then you need to have this way of abstracting away from the low level sensors into a high level representation that is easier to search in. And so I feel like we still haven't solved like this problem of how do you condition on the goal, kind of generate on the fly the right action and state representations. And I think that's probably the thing that we need to solve first, if you want to like connect those two.
Thanks so much. Any other questions? If not, oh, yes.
I have a question, but I want to ask the panel because I want so I'm all there.
Okay.
You just took about this case about this.
Do you think there is an algorithm that we should run for a billion years?
Yeah, I think we haven't found it. Yeah, I think we just haven't found it, but it's basically like when you think of like the scientific process, it's something that I want to see running forward forever. And so there are like stuff like that, that if we could get there, if we could have like a purely robotic AI scientific process that would give us like infinite technology, then yes, sure. But then yeah, you need to still like connect it to our problems. I mean, it needs to like be interesting. So in open-endedness, there's a novelty, and then there's a learnable and interesting. And so it needs to be interesting to us, such that I want it to run forever. And so that's why I think it needs to be, whatever it is, it needs to be collected to the human cultural evolution process in some way. It can't be like separated from that, otherwise it's sick.
Okay, thanks so much. And let's give another round of applause to